A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headache.
If you're building anything with AI, check them out. Modal.com. Imagine you are leaning over the open hood of a car, staring at a labyrinth of hoses, wires, and heat shields. Usually, you would be squinting at a greasy paper manual or trying to pause a YouTube video with your elbow while your hands are covered in oil. But now, you are wearing a pair of lightweight glasses, and suddenly, a shimmering three-dimensional arrow appears in the air, pointing exactly to the 10mm bolt you need to loosen. As you move your head, that arrow stays locked onto the bolt, and a small translucent window floats to the left, showing a real-time X-ray view of the belt tensioner hidden behind the engine block.
That is the promise of the spatial computing era, Corn. It is not just about having a screen on your face, it is about the brain behind the eyes. Today's prompt from Daniel is about the convergence of artificial intelligence and augmented reality, and he wants us to dig into 10 specific technical synergies that are turning this from a sci-fi gimmick into a fundamental shift in how we process information. I am Herman Poppleberry, and I have been waiting for this hardware-software handoff for a decade.
It feels like we finally hit the inflection point. Between the Apple Vision Pro developer kits that rolled out in February and Meta's Orion prototypes, the hardware is finally catching up to the dreams. But more importantly, the multimodal AI models, the actual logic engines, have reached a capability threshold where they can actually understand the world they're looking at. By the way, today's episode is powered by Google Gemini 3 Flash, which is fitting since we are talking about high-speed multimodal intelligence.
It is the perfect timing. If you look back at something like Google Glass in the early 2010s, it failed largely because it was a dumb display. It could show you a notification, but it didn't know what it was looking at. Now, we have shifted from simple computer vision to what we call world models. The AI isn't just detecting edges, it's interpreting context. We can categorize this into 3 layers: the perception layer, where the AI sees, the generation layer, where it creates the overlay, and the interaction layer, where it predicts what you want to do next.
I like that framework. It keeps us from getting lost in the cool factor and actually looks at the plumbing. Because let's be honest, if the plumbing has 80 milliseconds of latency, I'm going to throw up on my shoes.
You hit the nail on the head. Latency is the silent killer of AR. If that virtual arrow lags behind the engine bolt when you move your head, the illusion breaks and your inner ear revolts. That brings us to the first big synergy, real-time semantic segmentation. This is where the AI identifies objects and the AR highlights them. In February of this year, NVIDIA released their AR segment API, and the big breakthrough there was achieving 12 millisecond latency on mobile GPUs.
12 milliseconds is wild. That is basically instantaneous for the human eye. Most previous solutions were hovering around 80 or 100, which feels like the digital world is trailing behind the physical world by a noticeable ghosting effect. How are they shaving off that much time?
They are using a technique called pruned transformers. Instead of running a massive model that tries to understand the whole universe, the API uses a highly optimized, smaller model that focuses specifically on the spatial features in your immediate field of view. It is doing foveated inference, meaning it prioritizes the highest resolution processing on exactly where your eyes are focused. It identifies MacBook Pro 2021 or copper pipe half-inch and creates a mask around it so the AR system knows exactly where the boundaries of that object are.
But how does it handle overlapping objects? If I'm looking at a cluttered desk where my laptop is partially covered by a notebook and a coffee mug, does the segmentation get messy?
That's where the semantic part of semantic segmentation really earns its keep. Older systems would just see a blob of pixels. Prune transformers use a hierarchical approach. The AI understands that the mug is a distinct entity with its own depth profile, even if it's occluding the laptop. It creates what's called an instance mask for every individual item. So, if your AR app wants to highlight just the laptop, it can mathematically subtract the mug and the notebook from the highlight zone with pixel-perfect accuracy. It's essentially Photoshop's Select Subjects tool, but running 30 times a second in 3D space.
So the AI is essentially tagging reality in real time. That leads perfectly into the second synergy Daniel mentioned, generative overlay creation. This isn't just about pre-made stickers. This is about using something like Stable Diffusion 3, which now has native 3D capability, to generate UI elements or diagrams on the fly, based on what the AI sees.
This is where it gets really Iron Man. Imagine you are in an empty room and you say, "Show me what this wall would look like with a 1920s jazz club aesthetic." The generative AI doesn't just slap a wallpaper image on the wall. It analyzes the dimensions, the lighting from your actual window, and the texture of the drywall, then it synthesizes a 3D mesh with globally illuminated textures. It creates a digital twin of the room's lighting, so the virtual brass lamps look like they are actually casting light on your real floor.
I tried a demo of something similar recently, and the weirdest part wasn't the visuals. It was the shadows. If the shadows don't match the sun coming through your window, your brain immediately flags it as fake. But if the AI can calculate the light source in real time, man, that is a lot of math for a pair of glasses.
It is a staggering amount of math. To get that right, the AI has to perform inverse rendering. It looks at the reflections on your coffee table or the highlights on your floor to work out exactly where the light bulbs in your room are located and what their color temperature is. Once it has that environment map, it can render virtual objects using the same lighting parameters. If you place a virtual glass vase on your table, the AI ensures the reflections in that virtual glass are actually distorted versions of your real living room.
Wait, so the virtual object is actually reflecting my real room back at me?
It uses a latent diffusion model to fill in the blanks of parts of the room the camera can't currently see, creating a 360-degree light probe. This is why the objects look like they belong there. Without this AI-driven light estimation, virtual objects look like they're floating in a vacuum. With it, they look like they have physical mass and are interacting with the photons in the room.
But what happens when the lighting changes? If I turn off a lamp or a cloud passes over the sun, does the virtual object flicker?
That's the temporal consistency challenge. The AI has to run a continuous loop of light estimation. If it recalculated from scratch every frame, the object would jitter. Instead, it uses a hidden Markov model to smooth the transitions. It basically says, "I see the light is dimming, let me gradually adjust the virtual shadow's softness over the next 5 frames. It's a dance between real-time responsiveness and visual stability.
That is a lot of heavy lifting for a mobile processor. That is why we are seeing such a push for Edge AI. You cannot send that data to a cloud server in Virginia and wait for it to come back if you want that jazz club to stay anchored as you walk through the room. You need the NPU, the neural processing unit, inside the glasses to handle the heavy lifting.
You really do. If you offload that to the cloud, you're looking at a round-trip time of maybe 40 to 100 milliseconds depending on your 5G connection. In the world of AR, that's an eternity. By the time the lighting data comes back from the server, you've moved your head 5 degrees, and the shadow is now in the wrong place. On-device NPUs are now hitting 40 or 50 tops tera operations per second, specifically so they can run these lighting and segmentation models locally.
Which brings me to Synergy 3, predictive gaze tracking. This is one of those hidden AI features that makes the whole experience feel like magic. The system isn't just following your eyes, it's predicting where they're going to go.
This is fascinating tech. They use transformer-based attention models to analyze your microsaccades, those tiny involuntary eye movements. The AI can actually predict where your focus will land about 200 milliseconds before your conscious mind even realizes you've decided to look there. By doing this, the AR system can pre-render the high-detail content in that specific area. It saves massive amounts of battery and processing power because it's not rendering the whole world in 4K. It's only rendering the sweet spot you're about to look at.
It's basically a cheat code for hardware limitations. I can't render everything, so I'll just guess where you're looking and hope I'm right. But since the AI is so good at patterns, it's right 99% of the time. But what happens when it's wrong? Does the screen just go blurry for a second?
It's a graceful degradation. If the prediction fails, the system falls back to a lower resolution render for a few frames. But the AI models are getting so sophisticated that they don't just look at your eye muscles, they look at the contents of the scene. If a bright red ball bounces across your field of vision, the AI knows there is a 98% statistical probability that your gaze will lock onto that moving object. It combines biological data with scene logic to stay ahead of your brain.
That's almost telepathic. But doesn't that require the cameras to be constantly staring at my eyeballs? Is there a risk of eye strain from the infrared lights they use for tracking?
That's a common concern, but the power levels are incredibly low, well below the threshold of natural sunlight. The real strain is actually cognitive. If the AI predicts wrong too often, your brain gets visual friction, which is why the model has to be so precise. They use synthetic eye data to train these models, simulating millions of different eye shapes and lighting conditions so the AI can track a blue eye in a dark room just as well as a brown eye in bright sunlight.
Now, what about language? Daniel mentioned real-time translation with spatial anchoring. That sounds like the ultimate travel tool.
Google did a demo of this back in January at CES. They had a person walking through a street in Tokyo, and as they looked at the signs, the Japanese characters didn't just turn into English in a sidebar. The actual letters on the sign appeared to peel off and be replaced by English text that matched the font, the color, and the perspective of the original sign. They hit 94% accuracy in real time.
That is Synergy 4, and the spatial anchoring part is key. Seeing a subtitle at the bottom of your glasses is okay, but seeing the translation on the object is a game changer. It removes the cognitive load of having to look back and forth between the world and the translation. You just read the world.
Think about the utility in a professional setting. If you're an engineer working on a German-made wind turbine and all the warning labels and technical specs are in German, the AI doesn't just translate them, it reskins the turbine. This uses a combination of OCR optical character recognition and generative AI to match the typography. If the original sign was weathered and rusty, the AI-generated English text will also look weathered and rusty. It maintains the visual truth of the object while changing the semantic information.
How does it handle handwriting, though? If I'm at a restaurant in Italy and the daily specials are scribbled on a chalkboard in messy cursive, can the AI handle that?
That's the vision transformer at work. Traditional OCR would fail there because it looks for rigid character shapes. Modern AI uses contextual decoding. It looks at the surrounding words to guess the messy ones. If it sees spaghetti and pomodoro, it can infer that the messy word in between is likely all. It's essentially doing the same thing your brain does when you're trying to read a doctor's prescription. It uses a large language model backend to ensure the translated sentence actually makes sense in the context of a menu.
Does it work for spoken word too? Like, if I'm talking to someone, do I see speech bubbles?
The leading research right now is actually moving away from speech bubbles and towards spatial audio translation. The AI isolates the speaker's voice, translates it, and then resynthesizes it in your ear using the speaker's original tone and pitch, but in your language. Because the glasses have spatial audio, the voice still sounds like it's coming from the person's mouth. It's the babble fish from Hitchhiker's Guide, but powered by large language models and beamforming microphones.
And to make that look real, you need Synergy 5 physics simulation for virtual objects. If I drop a virtual bouncing ball in my living room and it hits my actual coffee table, it shouldn't just pass through it or bounce at a weird angle. The AI has to predict the materiality of my furniture. It uses diffusion-based physics engines to say that is a wooden surface, so the ball should have this much friction and this much bounce.
This is a huge leap from basic collision detection. In the old days, the computer just thought table flat plane. Now the AI uses a material estimation model. It looks at the specular highlight on the surface to determine if it's glass, wood, or carpet. If you drop a virtual coin on a carpet, the AI knows it should thud and stop. If it's hardwood, it should ping and roll. It's simulating the acoustics and the kinetics simultaneously.
But what about something complex, like a liquid? If I pour virtual water onto my real desk, does the AI know it should flow around my keyboard?
That's where neural physics comes in. Instead of calculating every single drop of water, which would melt your processor, the AI uses a learned fluid simulator. It's been trained on millions of videos of water behavior. It hallucinates the correct flow based on the 3D mesh of your desk. It knows that the keyboard is an obstacle with gaps, so the water should pool around the keys. It's a visual approximation that is 99% accurate to the human eye, but requires 1% of the traditional computing power.
I saw a tech breakdown of how they handle occlusion there, too. Occlusion is just the fancy word for when the virtual thing goes behind the real thing. If my virtual pet runs behind my real sofa, and I can still see the pet through the sofa, the immersion is dead. It just looks like a bad 1990s movie effect.
That leads us right into the second half of our list. Synergy 6 is AI-powered occlusion handling using neural radiance fields, or NeurFs. This is the cutting edge of how AR understands 3D space. Traditionally, you needed a LiDAR sensor to scan the room, which is slow and low resolution. But Meta showed off a NeRF on-the-fly system in April that can reconstruct a dense 3D mesh of a room from just a standard camera feed in 30 milliseconds.
Wait, 30 milliseconds? I remember when NeRFs took like 2 hours to train. A single scene on a massive workstation. Now they are doing it in the time it takes to blink?
It is a massive algorithmic jump. By using instant NGP or instant neurographics primitives, they can create a volumetric map of your room almost instantly. This means the AR system knows that the sofa has a back and a front, so it can properly hide the virtual pet when it scurries behind the cushions. It makes the digital objects feel like they have weight and presence in our physical world.
How does it handle moving objects, though? If I'm playing a game and my dog walks across the room, does the mesh break?
That's the dynamic NeRF challenge. The AI has to distinguish between the static background, the walls and floor, and dynamic actors like people or pets. It runs a separate tracking loop for anything that moves. It basically carves out a hole in the 3D map where the dog is and treats that as a moving occlusion mask. It's incredibly compute intensive, which is why these glasses often have dedicated CV or computer vision cores that do nothing but calculate these depth maps all day long.
But what if the dog stops moving? Does the AI realize it's still an object, or does it try to merge it into the floor?
It uses object permanence logic. The AI tags the dog as a dynamic entity. Even if the dog falls asleep and doesn't move for an hour, the AI remembers that this specific cluster of pixels is an independent object, not part of the carpet. It maintains a bounding box around the dog. If you try to place a virtual coffee table where the dog is sleeping, the AI will actually nudge the table over and say, "Occupied space." It's treating the physical world with the same logic a game engine treats its assets.
It's the difference between a hologram and an object. But to make that object truly useful, it needs a memory. That's Synergy 7, contextual memory and personalization. If I leave a virtual sticky note on my front door to remind me to take the trash out, I want that note to be there tomorrow morning, and I want the AI to understand why I put it there.
This is where we see the intersection with vector databases. The AI builds a persistent world model of your environment. It's not just a map, it's a semantic database. It remembers that Corn likes his virtual workspace set up over the kitchen island, and Corn's keys are usually on the wooden bowl by the door. If you lose your keys, you can ask the AI, and it uses its spatial memory to highlight the bowl.
I would pay a monthly subscription just for the "Where are my keys" feature, honestly. It's like having a digital butler that never blinks. But how does it handle changes over time? If I move my sofa to the other side of the room, does the AI get confused?
It uses SLAM, simultaneous localization and mapping, with a temporal update loop. Every time you put the glasses on, the AI does a quick relocalization check. It compares what it sees now to its saved vector map. If it sees the sofa has moved, it doesn't just error out, it updates the database. It basically says, "Okay, the world has changed, updating coordinates for sofas to new position X." It's a living, breathing document of your home.
Does it remember people too? If my sister comes over, can the AI remind me that her birthday is next week when I look at her?
Technically, yes, though that enters a huge privacy minefield. But the contextual memory synergy is designed for exactly that. It links your contacts and calendar to your visual field. If you look at a plant and you haven't watered it in 3 days, the AI remembers the last time it saw you with a watering can and can surface a reminder. It's connecting your physical actions to a timeline of events.
I love the idea of the AI being a witness to my life in a helpful way. But talking to the AI is only one way to interact. Synergy 8 is gesture recognition with intent prediction. We've had hand tracking for a while, but it's always been a bit clunky. Did I mean to click that, or was I just waving at a fly?
Right, the gorilla arm problem or the accidental click problem. The synergy here is using few-shot learning to adapt to your specific movements. The AI learns your personal signature for gestures. Maybe your pinch to select something is a bit looser than mine. The AI adjusts its sensitivity to you. But the intent part is the real magic. If it sees your hand moving toward a virtual button, it starts to highlight that button or prepare the action before you even touch it, which again masks that feeling of lag.
It's reading your body language, basically. Which sounds a little creepy, but in the context of a user interface, it's the difference between a tool that fights you and a tool that feels like an extension of your hand. Does it use the cameras to look at my hands, or is it sensing something else?
Most current systems use a combination of wide-angle constellation cameras and infrared sensors, but the really advanced ones are incorporating EMG, electromyography, in the frames of the glasses or a paired wristband. This allows the AI to detect the electrical signals sent from your brain to your fingers before your fingers even move. When you combine that pre-motion signal with the visual tracking of your hand, the accuracy goes through the roof. The AI knows you're about to click before the physical movement is even complete.
That is Minority Report level stuff. But what if I'm just fidgeting? I tap my fingers when I'm nervous. Will the AI think I'm trying to open 40 different apps?
That's where the intent classifier comes in. The AI is trained on natural human motion versus command gestures. It looks for a specific velocity profile. A fidgety tap has a different acceleration curve than a deliberate selection tap. The AI also uses contextual gating. It won't register a click unless your eyes are also looking at the object you're trying to click. It's a multimodal confirmation system, eye plus hand plus intent action.
That's the ultimate zero latency interface. Now, what happens when I'm not alone? Synergy 9 is multi-user collaborative AR. This feels like the killer app for the workplace or gaming.
This is incredibly difficult technically. If you and I are both looking at the same virtual architectural model on this table, we both need to see it in the exact same spot, with the exact same lighting, even though we are looking at it from different angles. Spatial's 2026 platform is a great example of this. They use consensus algorithms to ensure that object persistence is identical for everyone. If I move a virtual wall in the model, the AI mediates that change across everyone's headsets so there is zero drift.
And if we have 50 people in a room all seeing the same thing, you need a serious amount of bandwidth and coordination. You can't have my wall being 2 inches to the left of your wall, or we'll never agree on where the door goes. How do they keep everyone in sync without a massive central server?
They use edge orchestration. Instead of every headset talking to a server in the cloud, they form a mesh network in the room. One device, usually the one with the strongest battery or processor, acts as the spatial anchor for the group. It broadcasts the ground truth coordinates to everyone else via a high-frequency local protocol like Wi-Fi 7 or ultra-wideband. The AI on each device then does the local adjustment to make sure the perspective is correct for that specific user's head position.
But what if one person has a slower headset? Does the whole world slow down for everyone else to keep things in sync?
No, they use asynchronous time warp. Each headset renders at its own maximum speed, but the AI warps the image to match the latest global position data. If my headset is faster than yours, I might see a smoother animation, but the object will be in the exact same physical coordinates for both of us. It's like a multiplayer game where the server is just the air between us.
So it's like a local orchestra where the lead headset is the conductor. That makes sense. And finally, Synergy 10, automated content generation from the environment. This is the procedural aspect. The AI scans your room and says, okay, I see a flat table, a chair, and a rug. I am going to generate a tabletop game that fits perfectly on this specific table size. It uses the spatial reasoning capabilities, something we've seen in models like GPT-5 to understand the affordances of your furniture. A table is for placing things. A floor is for walking. A wall is for hanging things.
This is where semantic understanding meets creative AI. If the AI identifies a bookshelf, it doesn't just see a block of wood, it understands the concept of a bookshelf. It might suggest turning your real books into a virtual library, where the spines animate when you look at them. Or, if you have a window, it might suggest a virtual weather overlay that shows a tropical rainforest outside instead of a rainy Tuesday in Seattle. It's using the physical geometry as a seed for generative creativity.
It's like the world becomes a level in a video game that builds itself around you. I love the idea of the AI looking at my boring living room and saying, you know what? This could be a medieval castle if we just tweak the lighting and add some virtual stone textures to the walls. But how does it know what fits aesthetically?
It uses style transfer models. You can give the AI a prompt like cyberpunk or Victorian, and it uses its understanding of those aesthetics to reskin your environment. It knows that a cyberpunk aesthetic requires neon strips along the edges of your furniture and a gritty texture on the floor. It's not just random, it's applying a consistent visual language across all the objects it has identified in the room.
It turns the entire physical world into a canvas. But Herman, we have to talk about the elephant in the room that Daniel touched on in his notes, privacy. For all 10 of these synergies to work, your glasses have to be always on and always watching. They are mapping your house, your family, your habits, and your belongings in high-definition 3D.
Yeah, that is the privacy utility trade-off. To get the Where Are My Keys feature, I have to let a corporation have a 3D floor plan of my bedroom. That is a tough pill to swallow for a lot of people. I think we're going to see a huge divide between companies that do on-device processing, where the data never leaves the glasses, and companies that try to suck all that spatial data up into the cloud.
What's the technical safeguard there? Can we actually prove the data isn't leaving the device?
Apple is already leaning heavily into that with their on-device differential privacy framework for AR. They use secure enclaves where the spatial mapping happens. The map of your room is converted into a mathematical hash that is useless to anyone else. Even if a hacker got into the cloud, they'd just see a string of numbers, not a picture of your living room. They want to prove that the AI can understand your room without the person, at Apple, knowing what your room looks like. It is a massive technical challenge, but it might be the only way people accept this tech long term.
There's also the social aspect. If I walk into a cafe wearing these, everyone else in the cafe is being mapped by my glasses. That's a whole different level of privacy concern.
That's the passive consent issue. We saw this with Google Glass and the Glasshole era. The difference now is that the glasses look like normal Ray-Bans or Wayfarers. To mitigate this, manufacturers are building in physical privacy indicators, like a bright LED that can't be disabled by software whenever the cameras are active. But more importantly, the AI can be programmed with privacy masks. The system can be designed to automatically blur out human faces or sensitive documents in the memory it stores, so even if it's mapping the room, it's not seeing the people.
It's funny, we spent decades trying to get computers to understand code, and now we're spending billions to get them to understand reality. It's a complete reversal.
It really is. And for the developers listening, the takeaway here is that you can't just be an AR developer or an AI developer anymore. Those silos are gone. If you're building an AR app today, your baseline hardware is something like the Qualcomm Snapdragon XR2 Plus Gen 2. That chip is designed specifically to handle these neural workloads alongside the graphics rendering. If you aren't utilizing the NPU for things like hand tracking or scene understanding, your app is going to feel like a toy compared to the native experiences.
So, step 1 for any builder is to lean into the semantic APIs. Don't try to build your own object recognition from scratch. Use the high-speed, low-latency hooks that NVIDIA or Apple are providing. And step 2 is to respect that 20 millisecond motion to photon latency wall. If you cross that, you've lost the user.
That 20 millisecond rule is the golden rule of AR. Everything we've talked about, the predictive gaze, the edge AI, the NIRFs, is all just a sophisticated way to stay under that 20 millisecond limit while making the digital world look as solid as the physical one. If you fluctuate to 30 or 40 milliseconds, the user might not see the lag, but their vestibular system will feel it. It leads to what we call sim sickness.
I've had that. It feels like a very high-tech version of being seasick. It's not fun. So the AI isn't just there for the cool features. It's actually a safety feature to keep us from getting nauseous by predicting our movements and smoothing out the render.
It's the invisible glue. Without the AI, the AR is just a jittery overlay. With the AI, it becomes a new layer of reality.
I think the most exciting part is the proactive AR shift. We're moving away from pulling information like searching for something on your phone to the AI, pushing information exactly when you need it. If I look at a plant and it looks a bit wilted, the AI should just whisper in my ear, "Hey, that's a peace lily and it needs water." I didn't ask, but the AI knew I needed to know.
It's ambient computing. The interface disappears. You aren't using a computer, you are just living your life with a slightly upgraded version of reality. Imagine walking through a grocery store and your glasses highlight the specific items on your list, but also flag the ones that contain allergens you're sensitive to. You don't have to read the labels. The AI has already read them all for you.
Or even better, it shows me a virtual path on the floor to the exact shelf where the peanut butter is located. No more wandering down the international foods aisle for 20 minutes looking for one jar of tahini.
That's the semantic search of the physical world. It's basically Control plus F, but for your life.
A reality plus, if you will. Though I hope it doesn't start showing me ads on my cereal box. This cornflake is brought to you by... No thank you. Can you imagine the ad-supported version of these glasses? You're trying to have a conversation and a virtual billboard for car insurance pops up over your friend's face.
That is the nightmare scenario. Spatial ad blocking is going to be the next big industry. We'll need AI firewalls that specifically filter out unwanted digital content. Imagine a world where you have to pay a premium to not see virtual advertisements in public spaces. It's a very Black Mirror concept, but technically, it's entirely possible.
We'll be installing AdBlock for the eyes within the first week. But seriously, the winners in this space won't be the ones with the best screens. They'll be the ones who master the synthesis. The companies that can make the AI brain and the AR eyes work together so seamlessly that you forget you're even wearing glasses.
It's about the frictionless experience. If the AI is smart enough to know when to be quiet and when to show you something, it becomes an extension of your own cognition. That's the ultimate goal, cognitive augmentation.
Well, I'm ready for my jazz club, living room, as long as I don't trip over my real cat while trying to pet a virtual one.
That is a very real risk, Korn. Always mind the cat. The AI might be able to map the cat, but it can't stop the cat from moving right under your feet the moment you put the headset on.
Wise words. The cat is the one thing AI still can't predict. Well, I think we've covered the map on this one. Thanks to Daniel for the prompt. This was a deep dive I've been wanting to take for a while.
It's a massive topic. We could probably spend an entire episode just on the NERF physics alone, but the 10 points Daniel laid out really give a great bird's eye view of where we are in 2026. It's no longer about whether AR will happen, it's about how quickly we can integrate these AI models to make it usable.
The hardware is here, the models are here, now it's just down to the developers to build the glue that connects them. I'm looking forward to seeing what the next 12 months bring in this spatial space.
It's going to be a wild ride. Just keep your eyes on the road, or at least the virtual version of it.
Before we go, I have to ask, what's the one piece of legacy tech you think this kills off first? Is it the smartphone or the laptop?
Honestly, I think it kills the television. Why buy a 75-inch piece of glass that hangs on your wall and consumes 300 watts of power when you can have a virtual 200-inch IMAX screen that follows you from the living room to the bedroom? The moment the resolution hits retina level in these glasses, physical screens become obsolete.
I can see that. My living room would certainly look a lot cleaner without a giant black rectangle dominating the wall.
Space becomes software.
Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power the generation of this show. Without that serverless muscle, we wouldn't be able to process these scripts at the speed of thought.
This has been My Weird Prompts. If you are finding these deep dives useful, leave us a review on Apple Podcasts or Spotify. It really helps the algorithm find other curious minds who want to look under the hood of the future.
Or find us at myweirdprompts.com to see the full archive and all the ways to subscribe. We'll be back soon with more weirdness.
See ya.
Later. Later. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts.